Okay, so let me put it in full screen. Okay. Yeah, so firstly, do you all know optical fiber? Do you know just name?
Yes.
Okay, so probably some of you your home already use fiber to the home technology rather than coaxial couple technology before. So we get high speed internet, higher speed internet. So fiber to the home is we call the FTTH. So optical fiber plays a role to get internet, get connected from the central office to home. So before fiber to the home, people began to use optical fiber in telecom from long haul and NOC application to connect countries, or in a country connect cities, like from Los Angeles to San Francisco. There are some possibility using optic fiber to connect from the land or through the NOC. So we call it submarine optical cable. And so optical fiber, it's a technology that can transmit signal from one place to another place. It can transmit the optical signals while light in fiber more than 100, even 200 kilometers without any kind of like relay or amplification. So it's quite a useful technology. Basically, it's enabling technology for internet. So make high speed, high traffic possible. Then parallelly, in the research area, people begin to find some kind of we call bad effects. That's mostly non-linear effects, optical effects. It means it can bring some noise from the environment physically, such as temperature can bring kind of noise. We call the Raman effect. It's a non-linear effects. And also there are some others like dispersion and blurring. So these are bad effects for telecom, because telecom, we try to transmit optical signal from one city to another city without any distortion or noise. But nonlinear effects and other optical effects can be affected by the environment parameters such as temperature, vibration, to bring noise into the signal. So it's not good for telecom. But from another angle, we try to use all these effects to detect the environment. So it could be very useful for sensing technology to sense the environment. So here we have some major technology used in fiber optic sensing technology. So actually, there are more other optical effects are under research and development to be used for other kind of detection. So we have called a distributed temperature sensor. In short, it's a DTS. So this one is just technology using the measurement of Raman backscattering, and also we use optical time domain refraction as another platform to get the information along the fiber, because even the speed of light is so fast, but we still can identify how much time the light approach to one location and a far location. So we can identify the very subtle difference between the two time delay, so we can locate where's effect happening. So basically, we can get 1 meter under 1 meter spatial resolution. So another name called FBG. So it's another optical effect we call the Bragg refraction, and so the fiber with Bragg grating, so we call this FBG. So FBG technology can be used for temperature and strain monitoring or detection. So actually, fiber Bragg grating is my topic for my master degree 20 years ago. Yeah, it's more than 20 years ago. Yeah, so FBG is also very useful fiber optic sensor for fire detection and for strain. So strain monitoring is very important in civil engineering. Later, I have some projects examples. And the DTSS, it's the sensor for strain, temperature strain. But for Brilliant backscattering, this effect is a little bit tricky because temperature mixed with strain. So Brilliant backscattering have two effects mixed. So in some application, we should differentiate from the temperature from strain, but sometimes we want to monitor strain. So we try to get rid of the temperature effects from just Brilliant backscattering. So a little bit of conflict, but we can get more information on this. And finally, the DVS and the DAS or DAS. V stands for vibration. A is acoustic. So vibration or acoustic, just a difference between the because of the range of frequency. Vibration is basically a lower frequency, but acoustic means higher vibration frequency. And this one is based on really coherent noise. And this is also the latest technology and commercialized for some industries. Okay, so little more details in Rayleigh, Raman, and the Brilliant scattering. And so if we put a laser, the light, into an optical fiber, we get some scattering already. It's ready without any wavelength shift. So probably a little more explanation about a light, the basic performance of a light. So light, we understand that there are different color of light, red color or blue color or infrared. So red has longer wavelengths than blue. Blue is longer than UV, and green is in the middle between blue and the red. So longer than red, we call it infrared. Then go to the short wavelengths. We have UV, then even deep UV, and so frequency frequency multiply wavelengths equals to the speed of light. So in free space, basically the speed of light is about 300,000 kilometers per second. So it's the speed. But if we have the light transmitting in glass, like optical fiber is it's made of glass. In glass, the speed is a little bit slow. In free space, it's the fastest. And then what if you transmit water, light in water? Water have a different index. So frequency, you can understand the frequency as wavelengths because it's a pair of the parameter. So higher frequency stands for shorter wavelengths. And so you can see Rayleigh backscattering has zero wavelength shift, but blurring and blurring Stokes anti-Stokes wavelength shift is about 11 gigahertz frequency shift, and the Raman has more. So it's not necessary for you to remember all these effects. Just have a basic concept in mind. Non-linear effects means wavelength shift, but if it's linear effects like Rayleigh, it's without wavelength shift or frequency shift. So it's kind of like a very basic understanding on this. And the DTS is based on Raman, and so it's a temperature sensor. So from the DTS, we have the light, the photons coupled into optical fiber. Then the light transmit forward and get back scattering in the back direction. So we have receivers here, photo receivers here to detect the photon and give some judgment on the temperature. So this is a more detailed module level schematics about the parts, the components inside the DTS. So basically, we have laser. Then after the optical filters, we couple the light into the optical fiber. This blue block stands for optical fiber. Optical fiber can be as long as like kilometers, hundreds meters, kilometers, even 10 kilometers or 30 kilometers. And when the light transmits forward, we always get a back scattering from each point along the fiber. So when we detect the refraction, the back scattering, we will put the optical the light into optical filters, and we can differentiate the Stokes or anti-Stokes, basically two different shifted wavelengths. Then we use a pair of APD. Its APD is a photon detector to measure the photon, to measure the power level and the frequency from the back scattering. Then we have a lot of electronics and software to do some calculation based on the data we received, and finally we have the temperature data. Then application and the customer, they use the temperature data to monitor cable, to monitor pipeline, for fire detection, or just for temperatures, for industrial status monitoring. Yeah, so finally, it looks like this. The laptop PC is not necessary. The system, the box can work standalone. So in the black box, we have laser, we have APD, we have optical filters, and other optical components to have the light source and to couple the fiber to get the refraction to or back scattering and differentiate the wavelengths and put the lights into photon detector. And after photon detectors, there are more analog electronics thing than digital electronics and the software. So in this black box, we have optics, hardware, and the software. So it's a standalone working system, can monitor the temperature from outside cable, fiber optical cable, and give alarm, give the trigger to the relay, and from relay connecting to industrial system. So we can see up to now we can already monitor through one box. We can monitor 30 kilometers, and the measurement time is 3 seconds to the whole 30 kilometers. And the spatial resolution we call this positioning accuracy is 1 meter. So we can locate, we can know, finally we can understand the temperature data 1 meter based. And the temperature accuracy can reach 1 degree C accuracy. And the total power consumption is quite low. It's just like a PC, maybe a little bit more than a PC. It's only 70 watts. Okay, so we will have this unit in Idea Lab, and this time we ordered 5 short distance, 500 meters units, and 1 unit of 30 kilometers. I think 5 maybe. I'm not quite sure. 5, but 5 kilometers is already long enough for most of our application. Okay, so in DTS, it can be used for fire detection industry, especially in tunnels, the long linear assets monitoring. And the DTS also can be used for power cable monitoring. And later I can show you some field picture for how to use optic fiber in power cable monitoring. Then other applications in industry, like pipeline leak detection, because leak from a pipe, it's from high pressure to low pressure. This physical effect can, something like it can bring the heat from the leaking point. So you can monitor the temperature to understand how big the leak is. Then monitoring, like huge size, bigger size dam, there are always seepage through the dam. Even it's quite thick, quite a bigger size, but there are always seepage. We call the leakage, water leakage in the structure, a lot of leakage in the structure. So we can use temperature data to understand where the leakage is happening, and the other industrial processing. And the fire detection application, others. So this is how to attach the cable. So probably it's also important to understand if you in the future want try to deploy the cable along a structure in a building, in a campus building, you need to find out how to attach. So this is one of the method, but definitely you can find a different way to put a cable. So it's a cable tie to attach to a structure. Then the structure can be bonded to a pipeline, or could be a structure to a building. So this is the high voltage cable underground. In city, basically people use optical, use tunnel to accommodate the high voltage cable. It's very high voltage, could be like hundreds K watts, and So the blue line is the optical fiber. Yeah, so people can use the optical fiber to monitor the surface temperature of a power cable. So this is the optical fiber, and this is the optical cable. And so outside of optic fiber, there are some plastic tube and the Kevlar strands to protect the optical fiber from stress. And also we have outside protective coating. Mostly it's a rubber or plastic, but sometimes we need it can prevention from the fire. And in power cable industry, the most information the customer want to understand is the couple conduct, the temperature of just one, the conductor, and but there are different layers outside of the couple, so we need an algorithm to calculate from surface temperature to the conductor temperature. So it's also another interesting area. So for some applications, the direct temperature we detected, such as like surface temperature, is not good enough. We need to develop the algorithm using software to get to conclude the temperature another place. Yeah, so this is the curve, the calculated temperature and the actual temperature. So this is a fiber Bragg grating sensors I mentioned at the beginning. So how to fabricate FBG sensor? It's more complex than DTS. DTS just use commodity optical fiber. We don't need to do anything along the fiber. It's just the fiber. But FBG need a UV laser, UV light to fabricate, to print a grating in the core of optical fiber. So this is in the process of UV light, UV laser printing. Then after that, it have the optical fiber. The core will have permanent index change. So it will have the structure, microstructure in the core of the optic fiber. So this structure can reflect the light. So, and this structure is related to strain and the temperature. So we can use the optics to monitor the reflection change to get the outside the temperature and the strain along the fiber. There are some equations, it's quite simple, straightforward mathematics to calculate from the wavelengths to strain, or from the wavelengths to the delta T temperature difference. So yeah, but for this stage, we will not have FBG sensor in ID lab. But we need to know there are other fiber optic sensors called FBG sensors. So this is a microstructure, and when strain or temperature change, the central wavelength of the reflection will change. So from the wavelengths, we can get the temperature information or the strain information. Okay, so that's a box looks like from outside, and with the display, and we can get multiple point temperature and the strain information. And the DVS, so we'll move to the third topic, the vibration sensor or acoustic sensor. So this sensor just work like an array of vibration sensor to hear, to listen the outside of vibration or voice. So frequency range is from 1 Hertz to 1K. So basically, people for human being can hear. I think if I remember right, it's from like something like more than 10 Hertz to multi-K, but maybe 1K is the most. It's the highest frequency for human being can hear. If any higher than 1K or maybe even high, we call it ultrasonic. So ultrasonic people cannot hear. So DVS, maybe I skip all these bolding, go to the display. So from here you can see the vibration just is a distance and just is a time scale. So maybe I will show you a video later to better understand. Just is not very good to understand. And oh, maybe it's a video. Okay, I share sound already. So walking can give the signal on the display. It's a walking. The fiber is under the label here. Then you see the walking, the steps make the vibration. The vibration transmitted to the fiber. The fiber can detect, and the back scattering signal will be recovered by the electronics and the software. So finally, we get the data displayed here to understand its steps. So based on the frequency and the amplitude, the users, the people can understand if it's a human being walking or it's an animal or it's a digging, machinery digging. So get a lot of information from the vibration information. So these are different vibration signal from outside. Just when spread out quite a big range, because it's the meters, the distance. Just when it's long-lasting, because it's the time scale, for maybe seconds, for minutes, so different signals. So for DVS, we can use the just sensor for submarine cable protection. Submarine cable basically located at the seabed, and sometimes it's for like a offshore wind farm, and sometimes it's just for energy transmission, and inland we sometimes just is digging. If we want to protect the underground pipeline or cable from the damage of accidental digging, so this is the technology we can use. This is display the information from digging. Yeah, so we can detect people monitoring basically 5 meters long from the fiber, the cable. This is a pipeline, this is a cable. And for car driving, we can detect 10 meters away. But for machinery digging, we get a longer distance. It can detect 20 meters away. So, so this is a DAS. It's very useful in oil and gas industry, in pipeline. So these are the industrial standards we need to comply. And yeah. Then some real case. This is a case in Australia, and there is this kind of like accident happened. So the repairing cost is very high for the cable broken, and need a lot of labor and time to repair this one. So the damaged cable looks like this, but if we can use temperature sensor, we can prevent such kind of damage from higher loading. So we can keep the loading at the right level. So keep the cable from such kind of accident high loading. Okay, some field picture. This is a project we did during Olympic Games 28, and this is another project in Shanghai. And so put a lot of optic fiber along the metropolitan area and underground tunnel. And also we have the projects monitoring the industry, the transformers, substation in New Zealand and Australia. And it's the Spain project in Spain for fire detection. So it's kind of like I think it's for the coal transmitting for the coal shipping by convoys like a belt. And so it's a railway tunnel in Madrid airport. So we put optical fiber along the tunnel to monitor the whole space of the tunnel to keep it safe. This is another project in cable tunnel monitoring. It's for the cable for power grid. So it's another project to connect multiple points, the utility substation in India. And so just want to give you some ideas how to use the technology in real field. So this is for security. So this is an oil tank area to store the oil or gas. And so we put optic fiber along the fence. So we can detect the signal along the fence in certain distance. So we can monitor the activities. So if someone climb, and we can detect, we can alarm, we can trigger alarm. And also it can monitor the overhead line, high voltage power line. So when the ice too much surrounding the line, so it could be too heavy, and so need some kind of like a heating technology to melt down the ice, to get rid of the ice. So firstly, we need to understand the strain. If the strain is too much, so people need to take action to protect the overhead line. And the bridges, very tall bridges, and it's in the west of China, and very long bridges, and put optical fiber, FBG sensors in the structure before, during the construction. So after the construction, the sensor can output data of strain for a very long period, very long time. Could be like 20 years, 30 years. Keep monitoring the data, the strain data. So just as I would like to introduce, probably already take 40 minutes. So before we move to, so any questions for this presentation?
Yeah, so I was wondering about, you talked earlier about how the costs are too high for this to be implemented on a more residential or commercial scale. So, or for like, for example, in fire protection applications. So do you think that the costs that we'd have to overcome are, for example, like the costs of water damage to like other parts of a commercial building that we can like, locate where the fire is and not have to waste water in other parts of the building? Or like what further benefits can this technology provide to kind of offset the cost?
Yeah, so basically this is a quite long distance distributed sensor. Let me show back to the slide here. Yeah, okay, I couldn't find the best page to explain, but it just one. Normally one temperature sensor just can monitor one point, but this sensor we call this distributed temperature sensor (DTS). It means we can get quite a lot data. Every 1 meter we get one data. So if the application needs to monitor more than 1 point of temperature data, so it will be more cost effective. And another side, any kind of high tech, the cost will drop down strategically, dramatically, because the volume. So the difficulty right now for industrial application always has quite relatively small volume. Basically, now we deploy like hundreds to 1,000 systems in industry a year. It's already quite a bigger revenue, but in terms of volume, it's small. But for home or commercial application, the volume we talk about is KK, 1,000. So 1 million. In industry, we call the volume, say 1 KK stands for 1 million. So 1 million can bring down the cost strategically. So and after the technology are developed so many years, so the cost we are talking about from 10 years ago, we say one system needs like $1 million or hundreds K US dollar. Now the cost we are talking about is 10,000 US dollar. Like the compact unit we will have in ID Lab, we will have 5 units of access DTS. It only cover 500 meters, but the cost is around 2,000 US dollar. So finally, if we want to access home application, lower cost is the key to open this market. And the PC level cost, PC level price, I believe it's the key to open this market. So PC is from industrial computer, from workstations, then to desktop, to PC, and the cost dropped to like 1,000 US dollar, 1,000 to 2,000. So now what we can do is for short distance DTS, 500 meters range, we can do around $2,000. So it almost reach the range of affordable for home application. But for commercial, like for campus, for a small market, for a small building, it's already, I think, affordable already. Maybe for home, we should develop for the lower cost, maybe hundreds US$ will be a judgment for a home application.
Oh, I have a question as well. So while I was researching fiber optics and also when we were watching the video before everybody else joined, I saw and read that fiber optics has two things that can damage it per se, and one is changes in temperature, and the other is changes in tension, bending, stuff like that. And I see that your technology is very suited to detect changes in temperature. Is it also able to detect changes in tension, or is that a whole separate piece of technology?
Sorry, could you repeat the question again?
Yeah, I was wondering. I see that your technology is very suited in finding changes in temperature. Is it also suited in finding changes in tension, or is that a whole different set of technology?
Yeah, so different effects can for Raman it only can detect temperature, but for other so do you understand the vibration sensor we call DVS or DAS?
Yes.
So just is based Brilliant or just is based coherent Rayleigh. So you need to use different physics, different physical effect to detect different parameters, physical parameters. So in the research field, there are so many topics in the university or institutes to develop different technology for various parameter needs.
Okay.
Okay. So I